And we're back. Welcome, everyone. All right, so here it is. We're ready. We've set the stage. We've developed all the machinery that we need. We're ready to introduce the main star of Calc 1, and that's the derivative. So, in this lesson, we're going to see how to find the derivative of a function, and we'll see how to calculate this derivative at a specific point, and how to calculate the derivative so that we get kind of a function as a result, all using the limit definition of derivatives. So it's going to be good. Let's get into it. And here we go. We have our two slightly different versions for our limit definition of derivative. So let's look at the first one here, the derivative at a point. So it says f prime of a is equal to the limit as h goes to 0 of f of a plus h minus f of a all over h. And what we're doing here is a is a specific number. So what this formula is doing is it's calculating the derivative at one specific place at a. Well, it turns out that a lot of times we're not just interested in the derivative at one specific place. We're interested in the derivative at a whole bunch of different places. So instead of using a as a fixed number, we let a vary. We let a be a variable. So we kind of alter this definition, kind of generalize it a little bit. And instead of using a specific number a, we replace it with variable x. And this gives us the derivative as a function. So this gives us f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all divided by h. So that's really the difference here, is this formula is giving us the derivative at a specific point, and this formula is giving us the derivative where we get a function out. So when we calculate f prime of a, f prime of a is just a number. And as an example, what does this number sometimes represent? Well, as we saw in the last lesson, there's some applications for these limits. So a lot of times we think of this as the slope of the tangent line. So if we're calculating the derivative at a specific point, f prime of a, what the number represents is the slope of the tangent line. At x equals a, at that specific point. Now, if we were to calculate f prime of x, what do we get when we calculate f prime of x? Well, we actually get a brand new function. And there should be x terms there. A lot of times when we calculate the derivative, when we get a brand new function, there should be some x terms. And so the way to kind of think of what f prime of x is in terms of, say, slope of a tangent line, f prime of a is giving us the slope of a tangent line at one specific point. F prime of x then would be a formula which we can use to evaluate to find the slope at different points. So f prime of a gives us the slope of the tangent line at one specific point. F prime of x gives us a formula that we could then use to find the slope at a whole bunch of different points along our curve. So it's kind of handy to have this derivative as a function. Now, the process of actually calculating these limits, of actually finding the derivative, we call that differentiation. All right, so, you know, we've seen these limits before in the last learning outcome. Let's just remember what they were. So we've mentioned one. So slope of the tangent line at x equals a. And we said that was the limit as h goes to 0 of f of a plus h minus f of a divided by h. That was one of our formulas that we used. And that's one application. Another application we looked at is instantaneous velocity, and this involved the position function. So we looked at the instantaneous velocity at time t equals a. And what was this? Well, it was the limit as h goes to 0 of our position function evaluated at a plus h minus s of a all over h. So we saw these two different applications here, and it turns out there's, you know, a bunch of other applications too, depending on, you know, which field you're interested in, biology, economics, where these type of limit calculations show up. And so this type of limit shows up so frequently that we want to give it a special name, and we call it the derivative. So really that's what we're defining here. Pretty much in a lot of the examples we see, though, we're going to be considering either slope of tangent or instantaneous velocity, but we will talk about some other applications as well. Alrighty. Just get some practice working with these limits, setting these limits up, and actually working with them. All right, so example 1, let's differentiate the polynomial using the limit definition of derivative. All right, so our polynomial here is x squared minus 3x plus 5, and the degree of this polynomial is 2, the highest power of x there. You know, so you will be expected to be able to do this for polynomials with degree 2, polynomials with degree 3. Higher than that, you know, you can do it, but the algebra there becomes a little bit, you know, a little bit lengthy. So for the most part, the problems we'll be seeing for polynomials, at least, we'll be looking at degrees 2 and 3. But the process is the same if you have a polynomial of degree 4 or 5. Just the multiplication is going to take a little bit longer. All right, so how do we do this? We want to differentiate this function. And here we see the actual definition. F prime of x is the limit as h goes to 0 of f of x plus h minus f of x all divided by h. And as we're starting this, you don't necessarily have to do it the way we're going to do it here. And actually, after this example, I probably won't be doing it this way either. But until you get you're comfortable doing it, it doesn't hurt to kind of really step through the process like this. So what we're going to do is we're just going to start with f of x plus h. Just work with that. And a lot of times, this is where the mistakes get made. The rest of it's okay. We just want to make sure we're plugging in x plus h into our function correctly. All right, so we want to plug in. So let's go to our original function, and what we're going to do is wherever we see an x here, what we're going to do is we're just going to change that to an x plus h. So this x, I'm going to change to an x plus h. This x squared, it's going to become x plus h all squared. This minus 3x, instead of an x here, it's going to become minus 3 times x plus h. And then the plus 5 just stays a plus 5. Okay. So a lot of times that's the trickiest part, is just correctly plugging in x plus h. Now, let's do the multiplication here. So x plus h squared, multiply that out, and we would use FOIL for that. So you could think of it as x plus h times x plus h, write it as a product. And what we get is x squared plus 2xh plus h squared. And then let's distribute this negative 3. So when we distribute, we get a minus 3x, and then we get a minus 3h. And that plus 5 just stays a plus 5. All right, so there's our f of x plus h. We plugged in and multiplied everything out. And simplify. Sometimes there might be some terms that you can combine here. So simplify this as much as you can. This is about as good as we're going to get it. So now let's actually go to this fraction. And we're going to take this result and we're going to kind of plug it in for this fraction. So we're just kind of expanding our focus here. So we started with f of x plus h, and now we're kind of expanding outward and we're looking at this whole fraction. All right, so we're going to have x squared plus 2xh plus h squared minus 3x minus 3h plus 5. And I'm going to put that whole thing inside of a nice big set of parentheses there. Then we have subtraction. And then we have just our original function that we're subtracting off. So our original function is x squared minus 3x plus 5. Let's put that there. Okay, and then this is all over h. And the idea is we want to simplify this expression down. We want to simplify this as much as we can. And really it comes down to, let's do the subtraction. And a lot of times we get a lot of canceling that happens. So it's kind of fun. And the way you want, kind of an easy way to think of it, or maybe an easier way to think of it, is to start with the shorter end over here and just look for terms that show up on the other side. See if you can just cancel anything off. So I see an x squared here. I look over here, I see an x squared, and I'm subtracting. So I have x squared minus x squared. The x squareds cancel. Then I go, my next term, I have a minus 3x. Look around here. I see a minus 3x here. So whenever I have one thing minus the exact same thing, it cancels off. So I have a minus 3x minus a negative 3x. Those cancel. And then I kind of go to my last term here, 5. I'm subtracting, and then I look see if I have any other constant terms. I see a 5 here. So I have 5 minus 5. Those cancel. So a lot of nice canceling. All right, so what do we have left after all the action there? We have a 2xh plus h squared minus 3h all over h. See if we can keep going here. So we have each of these terms in the top has an h in it, so we can factor out an h. So I'm going to pull off an h there. And what do I have left over? Well, I'll have a 2x here. I'll have an one h left over here. And then I'll have a minus 3 left over from this. And then got a little bit more. A little bit more to cancel. Always kind of fun. H cancel. All right, so what are we left with? We're left with 2x plus h minus 3. All right, so once we get that fraction as simplified as possible, then we might go and actually calculate the limit. So we're doing the limit as h goes to 0. We worked with this fraction. We simplified it as much as we can. So now let's actually fill in our result. It's 2x plus h minus 3. Whoops, too many parentheses there. So we have 2x plus h minus 3. We're doing the limit of that as h goes to 0. And this is nice. This is a polynomial in terms of h. So we're doing the limit as h goes to 0. So it might seem weird. There's an x here, which we think of as a variable, and there's an h here, which we're also thinking of as a variable. But if we think about the limit that we're calculating, we're doing the limit as h goes to 0. So x isn't changing in this limit calculation. H is the thing that's changing. So we can view this 2x plus h minus 3, we can view that as a polynomial just in terms of h. So we can do direct evaluation to actually calculate this limit. And what do we get? Well, we plug 0 in for h. So we get 2x plus 0 minus 3, which gives us 2x minus 3. And there we go. We got our derivative. Nice. All right. That's the process. This one's not too bad. It's polynomial of degree 2. We'll spice it up a little bit. Just one other thing. Sometimes we call just this fraction, this f of x plus h minus f of x all over h. Sometimes we give that a special name. We call it a difference quotient. So we will be investigating that expression a little bit further in a few lessons. So that does have some significance as well. And we've seen that with secant lines and average velocity. So it does have its own interpretation as well. But we have our derivative, 2x minus 3 for this example. All right. Well, we've seen how to calculate the first derivative, but it turns out, what did we get? Well, when we calculated the derivative, we got a brand new function. So if we really wanted to, we could do it again. We could take this function and differentiate it. And so the process of differentiating, each time you get a brand new function, well, then you could just do the process over again, and you get what are called higher order derivatives. So for instance, the second derivative, we use f double prime. It's the derivative of the first derivative. Okay. And once you have the second derivative, well, you could figure out what the third derivative is. The third derivative, we use 3 primes there. It's the derivative of the second derivative. And you could keep going like this. So you could calculate all these higher order derivatives. For a lot of functions, you can just kind of keep doing this over and over. So you start with your function, you differentiate once, you get your first derivative, f prime. Take this now, this is a brand new function, take this function, differentiate it, you get the second derivative, f double prime. That's a brand new function, so take it, differentiate it, you get the third derivative, f triple prime. And then that's a brand new function, so you can do it again, but we stop using primes at some point because then it gets hard to read. So this is usually where we stop. So we might say use parentheses 4 to denote the fourth derivative, and then parentheses 5 if we were talking about the fifth derivative. So we can kind of keep this process going for a lot of functions. All right. So that's just a word about higher order derivatives. And then just a little bit about notation here for calculating derivatives. So there's kind of different ways to indicate the derivative. We've seen prime notation. So if we have a function y equal to f of x, we might say y prime or f prime. If we talk about the second derivative, we might use y double prime or f double prime. And we've seen what the prime notation looks like. There's kind of an alternative version for these and for prime, and that's Leibniz notation. And this is a little bit wordier. There's a little bit more going on here, but it's also more descriptive as well. So another way to indicate the first derivative is dy dx or df dx. This has the benefit of kind of telling us what we differentiated with respect to. So we differentiated the function y with respect to variable x. We differentiated function f with respect to variable x. So these are it's a little bit lengthier here, but you get more information about the derivative. And then we have this second derivative Leibniz notation, where we use these kind of twos to indicate the second derivative. So we've differentiated the function y twice with respect to x. Or we've differentiated the function f twice with respect to x. So we've gone through that differentiation process twice. So when you read this, these fractions are not really fractions. These twos aren't really exponents. So this is pure notation. So just a little warning here about our notation. It's just pure notation. So not exponents, not fractions. So when you see dy dx, you know, it's just one thing. It's not actually something divided by something else. It's just, that's the name of our function, dy dx. So these prime notation and the Leibniz notation, you know, all of these different cases down here, what we're really doing is we're just giving the name of that derivative. So in each of these cases, what these are doing, they're describing, they're telling us what the name of the derivative is. So if we have this function y equal to f of x, the second derivative, the name of that second derivative is y double prime. Or it's the first derivative, the name of that first derivative is dy dx. So it's just telling us the name of the derivative. We also sometimes use operator notation. So, and the way we indicate this is we'll have, you know, a bunch of x terms inside these big brackets, and then we'll have d dx, or our second derivative operator here, and then our big brackets, and then some x terms in there. And what these operators are telling us, these are directions telling us to differentiate everything inside the brackets. So if we had, say, an x squared inside here, what that would be telling us is take that function x squared and differentiate it with respect to x. Or take that function x squared and calculate the second derivative with respect to x. So the operator notation, these are really directions telling us to differentiate. So we have just different notations here. We have operators, d dx, that tell us to differentiate, and then we have just the actual names of our derivatives. So dy dx is the derivative of y with respect to x. So this different notation down here is the actual name of our derivative. And it turns out that once we have our derivative, we want to be able to evaluate in a lot of cases. And how do we indicate evaluation at, say, x equals a? Well, we sometimes use a vertical line. So, you know, if we had a function f of a and we wanted to evaluate at a, this is how we would denote that. But we could also write it as y, vertical line, which means evaluate at x equals a. If we had our first derivative, f prime of a, this means take your first derivative f prime and plug x equals a into it. We might also write that as take your first derivative dy dx and then evaluate at x equals a. So we're just plugging in x equals a. Again, the vertical line here means evaluate. And for second derivative, same kind of deal. If we wanted to evaluate our second derivative, take x equals a, plug it into f double prime, or we could write that as our second derivative, vertical line with x, meaning plug in, evaluate. So take your second derivative of y with respect to x and plug in x equals a. So we have different ways to denote evaluation for these different derivatives. And a lot of times you might see this evaluate line, big vertical line. All right. Let's try another one. Let's just get some practice now calculating derivatives. So here we're given a function. We're going to calculate the derivative of this function using the limit definition. Again, we see a polynomial here. The degree of this polynomial is 3. All right. So let's actually work with this. And we know from our limit definition, so let's write that first. Good habit, just to get into the habit of we're going to calculate the derivative. Let's write down the limit definition. So f prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. Just a good reflex to get into as soon as you see that phrase limit definition of derivative. As soon as you see that, just write down the formula. All right. Let's work with this f of x plus h though. Let's work with that. So we go to our function, and wherever I see an x, I'm going to change that to an x plus h. So I change this x to an x plus h. So I get right here. Then I'm changing this x to an x plus h. So I'll have an x plus h cubed. And then I'll have a minus 4. And then I'm going to change this x to an x plus h. And when we do this, you're going to have to multiply this out. Now there's kind of a few ways to think of this. You could go through the multiplication. Probably, requires the least amount of remembering things. So you just multiply it out. Probably that's what I would do. If you want to get fancy, another way to do it is the binomial theorem. It's getting pretty fancy, but it makes it quick. So that's another way to think of it. If you're going to multiply this out, what you would do is you would just rewrite that as x plus h times x plus h times x plus h, that cubed. So you just have to, multiply these two terms together, and then once you have those multiplied together, you'd multiply in this additional x plus h. So you're kind of going through the FOIL process there a few times. Not too bad. Something to do. So, this would be good practice just to show these steps. So we're not going to show this. But what you would end up with is x cubed plus 3x squared h plus 3x times h squared plus h cubed. And then multiply out the minus 4 times x plus h. So we get a minus 4x minus 4h. And sometimes we might be able to consolidate some of these, but nothing really, there's no similar terms here. So this is as good as we're going to get it. So, this might be a little tricky, just kind of multiplying all this out. Let's fill that in now for our function. So we're going to have the limit as h goes to 0. Let's take everything we just found. So x cubed plus 3x squared h plus 3xh squared plus h cubed minus 4x minus 4h. Put a nice sizable set of parentheses there around it. And then we're subtracting. And then let's take our original function, and we're going to subtract off f of x. So we're going to subtract off x cubed minus 4x. And then this is all over h. And we want to simplify this down. So you start with the shorter side here and just see if there's anything that kind of matches up on the other side. So we have an x cubed here and an x cubed here. Those cancel. So the x cubes cancel. And then we have a minus 4x here and a minus 4x here, and we're subtracting. So the minus 4x here gets canceled with that minus 4x there because of the subtraction. All right. So then we're doing the limit as h goes to 0 of, let's see what we have after all of this simplifying is done. So we have 3x squared times h plus 3x times h squared plus h cubed minus 4h, all over h. So we see that this term, nothing happened to. This term, yeah, we got everything. All right. So now, if we look at this, each term in the numerator there has an h in it. So we can factor out an h. So what do we get when we do that? Well, from the first piece here, we have a 3x squared left. From this piece here, we'd have a 3xh left. Then we'd have an h squared left over here. And then a minus 4 left over right here. So we factored. And then we want to cancel. So why are we doing factoring and canceling? Well, with all of these limit definition derivative calculations, we end up with a 0 over 0 indeterminate form. So we're going to have to do some algebra to get us there. And it turns out factoring and canceling is the way to go for this one. So we end up with the limit as h goes to 0 of 3x squared plus 3xh plus h squared minus 4. And let's do the limit of that as h goes to 0. And when we look at this, this is now a polynomial all in terms of h. We can view this as a polynomial in terms of h. So yeah, it's a little tricky here. There's x's and h's, but we look at our limit and it's h is going to 0. So h is really, in the context of what we're doing here, h is the really the thing that's changing. So this is just a polynomial in terms of h. So how do we do it? How do we calculate this limit? We use direct evaluation. So wherever we see an h, plug in 0. So we end up with 3x squared plus 3x times 0 plus 0 squared minus 4. And then this 3x times 0 is going to be 0. 0 squared is going to be 0. And so we end up with 3x squared minus 4. There's our derivative. Nice. All right. So you can see when we do this differentiation process, go through all this work, we start off with a function, and the differentiation process, calculating f prime of x, just gives us a brand new function. Should be x terms here. Now one thing when we do this, all of the h's should be gone. So once we calculate the limit, we're doing the limit as h goes to 0, our answer shouldn't have any h's in it. Those should all be gone. Only x's should be left. All right, let's take a little break. And we'll come back for this lesson. We'll do a few more examples, just a little bit harder, just for the additional practice. But really, we've seen everything we need to for these limit definition calculations for derivative. But we'll just try a couple other examples just for that practice. All right, we'll see you then.